Good afternoon, everyone. I'm Marcy Johnson. I'm the president of the Statistics Farmer Student Network at Texas A&M University. We're very fortunate to have today with us Dr. Scott Holan. Dr. Holan is a professor of statistics at the University of Missouri and a senior research fellow at the U.S. Census Bureau. His research focuses on high-dimensional dependent data modeling, machine learning for official statistics and survey methodology, and includes Bayesian methods, spatial and spatiotemporal statistics, and multivariate analyses, among many others. He's an elected fellow of the American Statistical Association, an elected fellow of the Institute of Mathematical Statistics, and an elected member of the International Statistical Institute. He currently serves as the co-editor-in-chief for the International Statistical Review, and he also was a recipient of the H.O. Hartley Award in 2016 and received his PhD under the advisement of Dr. Emmanuel Parson in 2004. Dr. Holan, the floor is yours. Please take over. We look forward to your talk.
Yeah, great, thanks. So I'll get underway here. This is I don't intend this to be very formal, so if people want to stop me, they can. I didn't really know what constituents, whether it be students or faculty or what have you, would join in. So just by way of background, I did graduate in 2004, and I've been at University of Missouri ever since. Interestingly enough, I didn't do any of the type of stuff during my dissertation that I do in this presentation. So in my dissertation, I did spectral domain time series with Manny Parson, but I did work on, as part of my research assistantship, I did work on analysis of complex survey data with some rural sociologists. And so that's related to this sort of methodology. Or the underpinnings of this sort of methodology. So today I'm going to describe computationally efficient Bayesian unit level models for non-Gaussian data under what's known as informative sampling. And this was motivated by the SAE, the Small Area Health Insurance Estimates Program at the United States Census Bureau. So this is an application to estimation of health insurance coverage, but in this presentation, we'll use the American Community Survey as a proxy for the SAE estimates. And I want to acknowledge the heavy lifters on this project. So a former student of mine, Paul Parker, he's now an assistant professor at University of California, Santa Cruz, and also a Schedule A employee or part-time census employee at the U.S. Part-time employee at the U.S. Census Bureau and the Center for Statistical Research and Methodology. And then also Ryan Janicki, who's a principal researcher in the Center for Statistical Research and Methodology at the Census Bureau. And I also have an appointment, a half-time appointment through an Intergovernmental Personnel Act at the U.S. Census Bureau in the Office of the Associate Director for Research and Methodology. So, I won't advance. Let's see. Okay. So as part of the fact that I have a partial appointment at the Census Bureau, I have to make the following sort of disclaimer, and that is that the views expressed are those of the authors and not those of the Census Bureau. And also, since we're using confidential microdata in this presentation, when you do an analysis or use methodology that uses the confidential microdata, in order to release those findings, you have to go through a disclosure review board. And so this is the disclosure review board number. So before I get underway here, one thing I'll describe is the motivations, because everybody comes to this with different backgrounds. So I'll describe some of the motivation of what we're undertaking here. And then once I've described the motivation, I'll get into the methodology or the methodological development. And then I'll show how this works or how effective this works through an empirical simulation study. And I'll describe what I mean by an empirical simulation study when we get there. And then I'll present some findings with the motivating example, which is an application to health insurance estimates. And then I'll conclude and take some questions. So just getting underway. So the motivation for this is as follows. So when you're in an official statistical agency, such as the Census Bureau or the Bureau of Labor Statistics or National Center for Health Statistics, oftentimes one of the goals is to produce small area estimates. And what you want to do when you produce small area estimates is to estimate a population quantity for a specific subdomain. So this typically relies on survey data, and traditional direct, or what they call design-based estimates, may have excessively high variance when we're talking about small areas. And when I talk about small areas, I talk about undersampled or unsampled domains. And so two big examples of this are the SAPE and the SAHE programs at the United States Census Bureau. So the SAPE is the Small Area Income and Poverty Estimates program. And that's actually something that's mandated by law, that they have to produce those estimates. And then the motivating example for this illustration is the SAHE estimates, and that's the Small Area Health Insurance Estimates program. So in the small area estimates domain, you could think about going about modeling in two different ways. So the first would be an area level model, and the next would be a unit level model. And oftentimes I think about these in two buckets. So like you could think about, what would I do if I'm at the agency and I'm trying to disseminate estimates to the public? And what would I do as a data user? And sometimes those are useful distinctions between how I would go about modeling. And sometimes they're blurred, right? Sometimes I'll do area level models, even though I'm at the statistical agency and have access to the confidential microdata. So an area level model is something where we treat the direct estimate, or this design-based estimate, as the response variable. So you can think of the direct estimate, like one example of that would be like a Horvitz-Thompson estimator, which is just a weighted total. And so you're incorporating the weights through this design-based estimator. And usually at an area level model, it'll incorporate some smoothing through the model. One thing that I've championed or been involved a lot in is using dependent data, so spatial modeling. And so you can think about incorporating smoothing through the use of a spatial model. And then one problem with area level models, at least from my perspective, is that they can require ad hoc, what they call benchmarking techniques. And those techniques are used to aggregate estimates across varying spatial resolutions. So as a data user, it's sometimes appealing to have all of the counties add up to the state totals, and then all of the state totals add up to the national estimates. But this is not really something that's realistic in practice, because those are estimates, and so there's uncertainty associated with each one of those estimates, and so there's no reason why those should be equal. And data users like them to be equal, so they force this through this benchmarking methodology. Another approach would be the unit level models, and that will be a situation where we treat the individual survey unit responses as the response variable. And in this context, there's a potential for more precise estimates. And this is a good paper, this Heteroglou and You, 2016. That's a good paper that describes some of the benefits of unit level models. And by using a unit level model, we can make predictions for all units in the population. And then since we have an estimate for all the units in the population, we can get estimates at differing spatial resolutions, and we can have a natural aggregation structure. So it's a bottom-up approach, and so things will be internally consistent by construction. So although there are some benefits to doing a unit level model, there's also some challenges. And one of the challenges is that they're more computationally intensive. So when you think about like how many people there are in the United States, that's certainly way larger than the number of counties or the number of tracts in the United States. And so the data sizes are orders of magnitude larger in the case of the unit level model. And also at the unit level, we don't have a central limit theorem. And so most data tend to be non-Gaussian. And then there's also a need to account for the survey design, and we'll describe that in detail as we go through this. If we don't account for the survey design, then we're going to end up with biased estimates, and that's undesirable. So when there's dependence between the response variable and the sample selection probability, so like there's a probability between you being in the sample and the response that's of interest, the survey design is said to be informative. And it's critical to account for the survey design under this informative sampling design when doing a unit level model. And oftentimes the sample likelihood is adjusted in some manner to account for this. And so one way of doing this is to use the reported survey weights that can typically capture the design information, and those are usually released by the statistical agency along with the unit level data if they release those data. So there are often public use microdata or public use files, and those those contain record level data along with associated weights. And if you're behind the firewall, if you have access to the confidential microdata, then you have access to the weights and the full data set. So one place that you can get access to these types of data is in an FSRDC, so a Federal Statistical System Research Data Center. I believe Texas A&M has one of those, and under certain circumstances, you can gain access to the data. And this paper, Parker et al., my former student, Ryan Janicki, and I have this overview of techniques to account for informative sampling. So this is a review paper on unit level modeling. So with that in mind, let me go ahead and describe the methodology that we proposed. So as I alluded to, there are several different ways that you can account for the informative sampling design. One would be to include all the design variables in the model. Another would be to regress on the weights, and there's different ways of doing that. One is the multi-level regression and post-stratification, or the Mr. P models or the MLP models that are produced by Gilman and others. And the other is this pseudo-likelihood. So this was introduced by Skinner in 1989 and Binder in 1983. And it's essentially just an exponentially weighted pseudo-likelihood. So here, this yi is the response value, and then the wi is the survey weight for unit I and the sample s. And if you have this pseudo-likelihood, then you can maximize it to construct frequentist point estimates of the quantity theta. So this type of methodology goes back to the 1980s and was done in a frequentist context. Back in 2016, there was a paper by Savitsky and Toth. This was an electronic journal of statistics paper. It's a really good paper. And they showed that the use of this pseudo-likelihood within a Bayesian model results in a pseudo-posterior distribution that converges to the population generating distribution. So there was some theoretical justification for using this pseudo-likelihood within a Bayesian context. Here, this W tilde represents the survey weights after scaling them the sum to the sample size. So once we've estimated these quantities theta, right, or these parameters theta in our model, then predictions can be made for the entire population via the posterior predictive distribution. And there's some description. This paper appears in the Annals of Applied Statistics. I believe it came out June of 2022. And so there's code and there's a description in the appendix on how to do this, but you can generate an entire population at each iteration of your MCMC from the posterior predictive distribution. So then you can aggregate those to any level of tabulation that you want to create population estimates. And so then at each iteration of your MCMC, you get an estimate for the population quantity of interest, and then you can get a distribution over the whole MCMC for the population estimates. So typically in small area estimation, at least at the area level and now at the unit level, area level random effects are modeled through a latent Gaussian process. in order to capture spatial dependence. And that's a pretty natural thing. These data are typically collected over different geographies and over different times and in a multivariate context. And so taking advantage of the dependence structure is often useful in improving the precision of the estimates that you're disseminating. So when you use this type of model, this log latent Gaussian process model, it's conditionally conjugate when you're in the normal response data case. As I alluded to before, when we're talking about a unit level model or the record level data, typically the data are non-Gaussian. So sampling from the posterior distribution can be difficult in this case. So there's a paper by Nick Poulsen et al. 2013, and I think this is the Bayes-Logit package. I'd have to look back at the exact name of the package, but they developed a Pólya-Gamma data augmentation scheme that allows for conjugate sampling under logistic models, and that uses the latent Gaussian process. So in this context, we'll have a way of improving our sampling efficiently in a Bayesian context. So the Pólya-Gamma distribution, so Poulsen et al. Defined this random variable x to have a Pólya-Gamma distribution with parameters b greater than 0 and c a real number. They denote that as Pólya-Gamma bc if x is equal in distribution to this quantity. Here, this gk is just an independent gamma distribution with parameters b and 1. And then they show that this quantity here on the left-hand side has the following form, where kappa is equal to a minus b over 2, and this this probability of omega is a Pólya-Gamma with parameters b and 0. And they also show that the conditional distribution of omega given psi is also Pólya-Gamma. So we'll see why in a moment that that's important. So if we look at the unweighted binomial likelihood, right, it has this form, which is similar to the equation on the previous page. And so one thing that you could see is that if you look at the pseudo-likelihood instead of the likelihood that's generated by this binomial, this unweighted version, it also has the same form. Instead, now I have a yi star instead of yi, and an ni star instead of ni, where yi star is just yi times wi tilde, and an I star is just ni times wi tilde. So it's this scaled version where it's scaled by the weights. And so the pseudo-likelihood given by 3 is of the same form as that equation on the previous page. And so we're able to sample from conjugate full conditional distributions using a binomial type pseudo-likelihood with a Gaussian prior distribution and this Pólya-Gamma data augmentation variables. So this is the model that we propose. It's this pseudo-likelihood mixed binomial model, and it's given as this model here. So typically, if I were modeling this binomial distribution conditional on p, then I would want to model logit of pi in terms of some variables xi, where xi represents a q-dimensional set of covariates, right? Beta is the q-dimensional vector of fixed effects. And in this work here, this phi I represents either an r-dimensional vector of spatial basis functions or an incidence vector that's a vector of 0 and 1s, which indicates which area unit I is going to reside in. So this form here that encodes the spatial dependence. And then I have a prior on eta conditional on sigma squared eta, and then we have a prior on beta, and these are chosen so that we end up with things that are computationally convenient. So I'm not going to go through all of the specific forms here. What I wanted to really convey by this slide here is that if we use the model set up on the previous page, then everything works out to be in a distribution of standard form and can be sampled from directly. These wi, this conditional distribution of wi, when I say it follows a Pólya-Gamma, we could draw these Pólya-Gamma random variables using the Bayes-Logit package that's on the CRAN website. So that's something that's maintained by Poulsen and others. and can be sampled from directly. So even for some applications, so you look at this setup on the previous page, and you think, okay, great. We have a way of sampling from each of the distributions directly, and so I can go ahead and use my Gibbs sampler, and things are going to be computationally efficient. And that's great for many applications, but for some applications, like the analysis of the entire United States, even just using the Gibbs sampling is going to be too computationally expensive to fit the model. And so a popular alternative to running a Gibbs sampler is the variational Bayes approach. And here's some good references on the variational Bayes approach. And essentially what you have is you have a class of distributions D, which is chosen for this Q star theta, which is an approximation to the true posterior. And then you use optimization techniques to minimize the Kullback-Leibler divergence between the approximate and the true posterior distribution. So we get this, this approximating distribution. And there's an important result by this Beal and Garamani, where they focus on a specific case known as the variational Bayes EM algorithm. So this is a paper in 2003 that shows that the approximating distribution can be factored into a product of global parameters and local latent variables. So with that factorization, you can set up an iterative approach to minimize this Kullback-Leibler divergence. And so this just shows how you would break things up. And so the takeaway message here is that if you have models that have fully conjugate full conditional distributions, as well as likelihoods from the exponential family, then these factorized approximate distributions are of the same class as their corresponding full conditional distributions. And so you could set up a very efficient variational Bayes algorithm. Okay, so there was a paper in 2019, this Durante et al., and they explore the use of the variational Bayes EM algorithm for logistic regression with this Pólya-Gamma data augmentation. And what we do is we extend their approach to work with this pseudo-likelihood mixed binomial model. And so the forms of each of these expressions aren't important. What I want to convey here is there's a very straightforward algorithm that can be done to sample from the variational Bayes distribution, or the variational Bayes approximation, and this just outlines how you would go about it. And as I said, we have some code on a public GitHub repository, as well as on the supplemental material for the Annals of Applied Statistics that does all of this stuff. So the interest in the example we're looking at is not really the binary case. Instead, we're more interested in the categorical case. So we're going to propose a multinomial model. So similar to this pseudo-likelihood mixed binomial model, we write the pseudo-likelihood mixed multinomial model. And so you can think about the previous model that we wrote down, how you would naturally extend that to the multinomial case, right? And so here we're modeling the PIK as this softmax, and then this psi-ik, right, has the same sort of form as in the pseudo-likelihood mixed binomial model. And then we have the priors on the other parameters. Here, we constrain beta k and eta k to be equal to 0 for identifiability purposes. And this k-dimensional vector zi is going to represent the number of successful outcomes in each of the k categories for survey unit I. And then this k-dimensional vector pi is going to represent the probability of being in each of the categories. So an important component of this model that we propose makes use of this result from Linderman et al. 2015. And what they show is that the multinomial distribution may be written as a product of independent binomial distributions. So this is this multinomial stick-breaking representation. And so the beauty of this is that once you've written down the model for the binomial distribution, you can extend it in a straightforward way to the multinomial case by using this stick-breaking representation. So once we can fit our pseudo-likelihood mixed binomial model via Gibbs sampling or variational Bayes, then we can easily extend that to the pseudo-likelihood mixed multinomial case. And so this just gives a formulation of the model for the in terms of the stick breaking representation. So this is writing it in terms of the product of these binomials. Okay, so once you have this methodology in place, you want to see how effective it is and how well it works in practice. And one good way to do this is through an empirical simulation study. So rather than creating synthetic data from a parametric distribution, what we really want to do is try to mimic the real survey setting where the truth is known. So what we do is we create an existing survey sample as our population. So we take the ACS, right? It comes from a sample. So we consider that our population. And then we subsample from that population in an informative manner. And what I mean is, and by an informative manner, is we want the response to be correlated with the probability of selection. And then what we'll do is we'll compare the model results from the weighted and unweighted direct estimators. That way we'll see, like, is there a difference between the unweighted and the weighted estimators? And that's usually an indication that we have an informative sample, because under an informative sample, the unweighted direct estimate will have greater bias than the weighted direct estimate. So it's a way of sort of checking, do we create a simulation that has an informative sample? So the motivating example for this methodology was the SAE, like I said, the Small Area Health Insurance Estimates Program. And it's an important use of the small area estimation that relies on the American Community Survey. So the American Community Survey, for those of you that are not familiar, replaced the decennial census long form in 2000, right? Well, 2000 was the last decennial census long form. The first year of the ACS was, after the test phase, was 2005. And they produced, for a period of time, they produced 1-year period estimates, 3-year period estimates, and 5-year period estimates. They now produce only the 1-year and the 5-year period estimates, but the 5-year period estimates are on all of the geographies. So the goal here is to estimate the proportion of individuals with health insurance by county for a number of income to poverty ratio categories. So the number of people within each IPR category, that's going to be unknown, so we have to create those estimates. Health insurance and IPR category then must be modeled simultaneously. And so the IPR categories under consideration are given by these different bins. There are these different categories. And then within each of the IPR categories, an individual may be categorized as either having health insurance or not. And so if you proceed in this way, then individuals end up falling into one of 10 distinct categories, and you can label those C10 through C51, where CJK indicates an individual being an IPR category, J for 1 through 5, and then the health insurance indicator K equals 0 or 1. So here, since we're using, so if I wasn't using the confidential microdata, I wouldn't have a 1-year period estimate for the ACS at all of the geographies, because the ACS is only available at all geographies for the 5-year period estimates due to disclosure limitations and data quality reasons. And so we treat the 2014 1-year ACS, we have the confidential microdata, ACS sample in Minnesota as our population, and then this with roughly 120,000 people across all 87 counties. So here what we're going to do is we're going to subsample using this Poisson probability proportional to size without replacement. So this is a paper that explains how this works, but each one of our data sets is going to have an expected sample size of 10,000. And then the size variables that we'll use, SI, is just going to be equal to this function. Here, this WI star is going to be the original survey weight for unit I after scaling it to have mean 0 and standard deviation 1. And this HI is going to indicate whether or not unit I had health insurance. And by setting it up this way, we'll end up with something that has an informative sample. So to construct health insurance estimates by county and IPR category, we're going to fit the pseudo-likelihood mixed multinomial model with the 10 categories that I just described. Here, this NI will be equal to 1 for all I. And then the XI, the covariates that we'll use, will consist of race category, sex, and an age category. And then this phi that I described previously will be a vector indicating which county unit I resides in. And then we'll repeat the sampling and estimation procedure 50 times to compare the mean squared error and the bias. So the results of the simulation are as follows. The first thing that you can notice is that in this case, right, the direct estimate, right, does better than just using the unweighted direct estimate in terms of MSE and squared bias. And that's to be expected, right? We have an informative sampling design, so taking into account the sampling design is going to produce better estimates than if we ignore it. And then the model-based estimates do better than the design-based estimates, and that's not surprising either, because we're borrowing strength across the different geographies using that incidence vector and by using a model. One thing to note here, the variational Bayes does slightly better than the MCMC, and that's at the cost of some slight undercoverage, not really too bad. I mean, the nominal rate is 95%, and the slight undercoverage here is a subject of future research, but we don't have a really good answer for why it did undercover. And then the time, though, that you could see here is dramatically improved over just doing an MCMC. So the model-based estimates are certainly preferable to the design-based estimates in this case. This just gives an indication of like the empirical mean squared error by county across the simulation-based estimates for the state of Minnesota. The columns here, those refer to all of the IPR categories, so that income to poverty ratio. And then the different rows are corresponding to the different methods. So the HT is the design-based estimator, that's the Horvitz-Thompson. And then we have a unweighted direct estimate, so that's also a design-based estimate, and then our model-based estimates. And you can see we do significantly better in terms of mean squared error across the 50 simulations, uniformly across all of the different counties in Minnesota for all of the different IPR categories using the model. So then we considered an application to the health insurance estimates program. And here, what we wish to create are health insurance estimates by county and IPR category for the entire United States. And this is similar to what's done, like I said, in the SAE program. So you couldn't really do this with just using a Gibbs sampler, because the sample size is roughly 4.5 million individuals over 3,000 counties that we consider. And so the computational efficiency is a major bottleneck in tackling this problem. And so although we had slight undercoverage in the simulation, this is really the only path forward if we want to do it simultaneously on the whole United States. So the approach that we took is we used the pseudo-likelihood mixed multinomial model, fitting the variational Bayes approach in order to generate these estimates. And again, we used the 10 response categories from the simulation and used NI equal to 1 for all I. And then we used the same covariates that we considered in the simulation. The difference in what we're doing here versus the simulation is we use spatial basis functions for phi instead of using an incidence vector. So here we use 307. So this is like the first 10% of the eigenvectors of the county adjacency matrix. So you can think of like a nearest neighbor county adjacency matrix. So counties that share an edge have a 1 in this matrix, and then if they don't share an edge, then they have a 0. And this is this is motivated by this Hughes and Horan paper in 2013 JRSSB, and also by some work that we did in Annals of Applied Statistics in 2015, based on these Moran's I basis functions, where the suggestion was to use the top 10% of the positive eigenvalues, or the eigenvectors associated with the top 10% of the positive eigenvalues. And this provides us a substantial dimension reduction of the parameter space. And then we sampled 1,000 independent draws from the variational posterior distribution in order to generate our posterior predictive distribution. To run this on the whole United States, where I was saying we had 4.5 million observations, and then 3,000 counties roughly, took about 17 hours. So here's the results. So in the left-hand column, you could see the direct estimator. And in the right-hand column, you can see this is the model-based approach of the proportion of the population with health insurance by county and by IPR category. So each of the rows indicates a different IPR category. And so what you can see is, we have generally the same pattern, but just a lot less noisy than the counterpart direct estimator here. And then if you look at the whole United States, so over all of the IPR categories, you can look at this is the direct estimator. And then here's the model-based estimates of the proportion of the population with health insurance by county for the whole United States. And then similarly, we have the ratio of the model-based standard errors to the direct estimate standard errors by county and by IPR category for the continental United States. Here, the counties that have no available direct estimate are shown in gray, and what you see is that all of the ratios are seemingly less than 1, indicating that our model-based approach is doing better throughout all of the IPR categories and across the continental United States. So with that, I'll just make a few concluding remarks here. So we developed a computationally efficient approach to modeling binomial and multinomial survey data under informative sampling. And here there's many ways that you can handle informative sampling. We used a pseudo-likelihood approach to account for the informative sampling. And then we took advantage of Bayesian hierarchical modeling to capture the spatial dependence. And the unique thing here is we used the Pólya-Gamma Data Augmentation method, and that allowed us to construct both a very efficient Gibbs sampling algorithm and then a variational Bayes approach. And we applied this to health insurance estimation by county and by IPR category. So there's some future work that we're working on extending this. One is misclassification. So if you misclass, you have measurement error within the different covariates or multi-type data. So you can have different responses. So you might have one that's you'd have a multivariate model, and you'd have one response being Poisson and one being normal, or one being Poisson and one being multinomial, and then incorporating temporal dependence as well. And there's some takeaways from this. One is that this work ends up illustrating that it's feasible to use unit level models to create small area estimates with non-Gaussian data, even considering the computational complexity. So this is something that could be utilized in an official statistical agency to produce estimates at scale, just from a computational standpoint. Estimates such as health insurance are useful to researchers and the social scientists, but also programs such as SAE and SAPI are also used to allocate billions of dollars in annual aid. So things like Title IV, medical assistance program, national school lunch programs, and others. And we've also developed some extensions to this using deep learning that highlight how complex survey covariates can be used to improve estimates. And this paper, I think, I know it's on the archive, it may be already on the early view. It's a paper that just came out in JRSSA for those that are interested. And with that, I'm happy to take questions. Thank you.
Thank you, Dr. Holan. Dr. Holan's agreed to entertain some questions. Does anybody have any questions?
Somebody raised hand.
Oh, yes.
Unmute or not.
Philip.
Hello. That was a great talk. I really appreciate your time. I really enjoyed that.
Yeah, thank you.
I wanted to know if you could get at this same sort of problem using some of the in-law techniques, the Laplace approximation instead of variational Bayes, or am I?
Yeah, you probably could. I mean, I'm not a big inlay user, although I did comment on the original paper in JRSSD, but I'm not a big inlay user, and that's probably due to the fact that some of their software is not easy to adapt to any specific situation. But in principle, you could probably do in-law, or I mean, I've used things like Stan for things like this, and it you know, at the size problem for the United States, it's not very efficient. It kind of chokes. But you know, maybe in-law would be a good choice. I just have never tried to get that to work.
Thank you very much.
Yeah, you bet.
Another question? Does anybody have a question?
I think there's some in the chat. Nope, that was.
I don't have the chat. Let's see the chat.
There's some references.
Any other questions? Doesn't look like we have any more, Dr. Holan.
Oh wow, I got off easy.
I guess Philip's clapping his hands.
No worries. Thank you.
That's awesome. Well, thank you very much for agreeing to give your presentation today. It's always very nice for our current and former students to learn what each of us are doing. So it's very valuable information. Thank you again.
Thank you. I appreciate it. Have a great afternoon, everyone.
All right. Take
Bye-bye.
care, everyone. Till next time.